So 8.3 talks a lot about just random events happening. Um, if I were to ask you to write out 10 flips of a coin, so I want you just to guess randomly what 10 coins would look like. So you'd be like a tail and then a head and then a head and then a tail and then a tail, then a head and maybe a tail and then a head and then a tail and then a tail and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that would be all of them. But the reality is when you actually take a coin and flip it, you're most likely going to get a run that looks something like this. And people are like, no, no, that's not right because 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Like, that's not right because the probability of heads, there should be 5 out of 10 in here because that's, 50-50 chance. If I take 10 flips, my expected value is 0.5 times 10, or 5 of those should be heads. Okay? Kind of like if I take a dice and I roll it 24, what's the expected value that I get a 3? Well, the probability of getting a 3 is 1 out of 6. So 1/6 of these, so this is expected value, by the way. Expected value is the probability times of the number of events that took place. So to get a 3, we would expect to get a 3 4 times. So if I'm writing down, like, I take some dice and I roll them and I get like a 1 and then I get a 6 and then a 5 and then a 4 and then maybe a 2 and then a 1 again. And then I get a 6 and a 5 and a 3 finally shows up. And then I get a 4 and a 2 and a 2. And I get a 1 and a 6 and a 6 and a 5 and then a 3 and then a 1. And then I get a 4, a 4, a 2, a 6, a 5, and a 6. Well, people look at that and they say, well, we expected to see 4 threes in here, and there's only 2. Okay, um, this this does happen. Okay, if you take a dice and roll them and you write down 24, the results from 24 times, you're not going to see that it exactly works out. Maybe you will, but most often the case, you do not get 4, 4, 4, 4, 4, 4. 4 ones, 4 twos, 4 threes, 4 fours, 4 fives, 4 sixes. It doesn't work out that way right off. Okay. But what happens is as we get a large group of numbers, so say if I did this 100 times, it would be much more close to being this 1/6 value. The larger our group of numbers, the closer it is to of our actual uh, experiment approaching what we would expect. Okay, so if I did this 100 times, I might end up with 49 heads and 51 tails. Okay, but it's going to be pretty close. I even might be 48 out heads and 52 tails. Okay, but it's going to be really close to 50 and 50. So realize when we look at things randomly happening, you're going to get strings of things together. Okay, it's not going to be this nice, oh, I only had two, I had a tail and a tail. This next one's got to be a head. No, it's going to be more like this because the ones before this, because I had 3 tails in a row, does not affect the probability of this fourth one. The probability of this being a tail is still 50%. Okay, it has not changed. Okay, a lot of people are like, they're like, oh, I flipped a coin 5 times and I've got a tail, a tail, a tail, a tail. This one's got to be heads. The chance of it being heads is much better. No, the chance is still 50-50. Okay, this is still a 50% chance that it could be a tail again. Now, if I did this 50 times and I only get 5 heads, I'd be like, something's wrong with your coin. Your coin is way off. You've got it somehow made so that it lands tail side up more often than heads, because that's just way abnormal. But anyways, just a kind of a thought on this kind of an idea of randomness. Okay, so this is we started to touch on this a little bit before school got shut down on us for the rest of the year. But let's look at the second one. I'm not going to do the first one on your 8.3 that says chapter 8 sample test questions, but let's look at the second one. It says, suppose you have the 26 letters of the alphabet on separate cards in a hat. Okay, so you've got this hat. Should have been an artist, huh? Not really. So we've got this hat, okay, and you wouldn't be able to see that line. You just see the hole in here, but hold on. There we go. So you've got this hat, and inside of this hat, you've got a whole bunch of little cards, okay? You've got all these cards sitting inside of here. You can see through the hat right now. You've got 26 of these cards in here, okay? So you got 26 of these cards in here that have the letters A, B, C, all the way down to X, Y, and Z. You pick out a card, write down the letter. Put the card back in the hat, mix up the cards, pick out another card, and so on. Write an expression for the probability that on your first 6 draws, your letters spell Hamlet. So you're going to have 6 draws. What's the probability that I pull an H out of here? Well, there's one H out of 26 letters. What's the probability that I pull an A out of here? 1 out of 26. What's the probability that I pull an M out of there? Still 1 out of 26. What's the probability I pull an L out of there? 1 out of 26. Probability I pull an E, 1 out of 26. And the probability I pull a T out of there, 1 out of 26. You have much better odds of pulling out the letters Ham than you do pulling out Hamlet. Okay? Just because 6 times in a row, you're going to multiply these together. So it's going to be 1 out of 26 over 6 is the probability of this happening. So when they say that, if you have enough monkeys hitting keyboards long enough, eventually they're going to type out the encyclopedia, that'd be a long chance. So this is so small, there's 9. What this e to the negative 9 means is I'd move this thing 9 places. So it'd look like this. 0.1, 2, 3, 4, 5, 6, 7, 8, 3. 1, 2, 3, 4, 5, 6, 7, 8, 9% chance. So is there a chance that it could happen? Sure. But it is so small, like this is tenths, hundredths, thousandths, 10 thousandths, 100 thousandths, million, 10 million, 100 million, billion. So you have a 3 billionths of a chance, if that's the way you say that. I mean, it's just not very good odds that that's going to happen. But anyways, that's what that means. The third one says, suppose you flip a coin. If it lands heads up, you go 1 unit to the left on a line. So if it says heads, you go to the left. If it lands tails up, you go 1 unit to the right. What is the probability that after 3 flips, you'll be 3 units from where you started? So, in other words, here's your start. It's saying after 3 flips, what's the probability you're either here or here? So for this to happen, you'd have to get tail, 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 or head, 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 right? So the probability of head, head, head is 1/2 times 1/2 times 1/2. Probability of tail, tail, tail is 1/2 times 1/2 times 1/2. So this is 1/8 of a chance, and this is 1/8 of a chance. So because we could either go left or right, I add these two together. So 2/8 of a chance. So there's a 25% chance that you could be all the way over here, all the way over here. So the important thing to realize is the probability of heads is 1/2, 1/2, and 1/2, and you multiply them together. And then because we have 2 separate events, that could work, we add those events together to get our probability. Okay. All right. Suppose the World Series is about to begin. Some clairvoyants get together and decide to each predict different win-loss patterns for the 7 possible games during the coming series. So we have 7 games, right? 7 games. That is, one might predict the first team will win the first 3 games, then lose 2, then win the next. How many clairvoyants would be needed before being certain that one of them would correctly predict the outcome of the World Series? So this is a 2-event thing, right? You either win or you lose. It's kind of like you either have a boy or you have a girl. Okay? Now, this is kind of an interesting question. I'll show you the easy way, but this isn't quite how this actually would work. Because once a team wins 4, they get 4 wins, they win. So you really don't need the 7 wins. So anyways, let's kind of, so the first team could win. So we're just going to go by the first team. It could win or lose. And then from there, so it could win the first game or lose the second game. And then it could win or lose, win or lose, win or lose, win or lose. So this is 3 games. 4 games, it could win or lose, 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 win or lose. Well, if it's won these 4, so if this has happened, it's done. Okay, so I don't need to keep track of those anymore. So now, win-win loss, whoops. They could win or lose, and now that one's done. They could win or lose, 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 win or lose. So now out of those, if it follows this path, those are done. And if it follows this path, those are done. If it follows this path, those are done. If it follows this path, win, loss, whoops, that one won't work. Win, lose, lose. Nope, that won't work yet either. This one. Win, lose, win, win, win. That one's done because they've got 4 wins. Okay, so these are all done. These ones that have lines down them. Same with this one. Lose, lose, win. Oh, I didn't do the next line. Lose. So that's why I think this is a fairly complex question that I don't believe that these people understood. Well, I'm sure they understood, but I don't think they looked at it this complexly. So there's the 4th loss on that one. And this one we wouldn't even need to worry about. So win, loss, that one's done. Win, loss, win, loss, win, loss, loss, win, loss, win, loss. That's only 3. So if we go this way, lose, win, lose, 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 that one's done. Okay, so that is 1, 2, 3, 4, 5 games. So 6 games. So this one we need to worry about. That one's out. And this one's out too because it has 4 wins. So as soon as they got 4 wins, that one's done. So then I just go here, win, loss, win, loss. So anyways, I don't think they were thinking of it being this complex of a problem. So now if we look at this, win, 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 loss, loss, win. This one's out. Win, win, loss, win, win. That one's done. Win, loss, win, loss, win. That one's gone. Win, win, loss, loss, loss. This one's out. Win, win, loss, win, win. That one's out. Win, loss, 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 win. So now we come win, loss, win, win, loss, win. That one's out. So anyways, you could go through this and you'd have to like count out how many each of these little spaces there are. Each, you know, like the ones that terminate would count as one. And then at the bottom row, once you get these ones, you know, then you just count each of these because one way or another, these are going to end up being done. Okay, so you'd have to be like, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So you'd have to count them all like that. So I think what they had in mind was that you just have to have 2 to the 7th is what I think. But that's an overkill because, like I said, once you hit 4, a lot of these are going to be done. So anyways, just that kind of shows you a different way to look at that. Give you some more thought process on probability of how many people you'd need to have to say one out of this many is going to guess correctly what this is. You'll see those odds all the time when it comes to the NCAA March Madness. There's like, okay, we have 64 teams. Who can guess? How many people would it take to guess the winners correctly out of all of this? And that one's a really tough one. That's a huge amount of people. So anyways, that's kind of the thoughts on 8.3. So like I said, 8.2 is really the main part of the lesson. This one I just kind of wanted to help you understand what randomness is and kind of, you know, this like Hamlet type thing, and if you had to write out what a random flip of a coin would look like, you know, you would get some runs and some things together like this. So anyways, that is 8.3.